give the proofs because they are easier, or maybe you have seen, and in case of difficulties, of course, I will explain. But remember, now our motivation is what? See, last time also I said that, for example, we have studied affine spaces. And as you saw in affine spaces, the way it is, the way we have presented is that it's a geometry there, and this geometry not only actions on a vector space, but any G set or any G space which is simple transitive, that will give us a geometry. And this geometry we were studying, and the missing in the geometry was the perpendicularity. And that is what I want to now start. I want to equip also affine spaces with the perpendicularity. And those that will lead us to the study of Euclidean spaces. So that will lead us to inner product spaces and the geometry which arise from the inner product spaces. And I will do it a little bit more general because the essential point which I want to stress is I want to do real and complex cases together. That is what probably it might be new to you, how to do things together. All right, so let me start. So as you see the title, Sesquilinear functions or forms, examples and dualities. And these examples are very guiding examples which I will recall. And one more thing that I made this comment earlier also, that things will work not only for vector spaces, but it will work for free modules or arbitrary commutative ring. So that also one has to keep this view in mind, that one can do similar thing by assuming your ring is, of course, the rings for us are all commutative rings with unity. And then instead of you know that modules may not be free modules, but in case if they are free modules of finite rank, then one can do such a study over arbitrary commutative ring. That essentially will lead to what one calls it linear algebra over commutative rings, which is very useful for many research problems which are still very active area of research. So all right, so let us start precisely what we want. So as I said, V. So let V be a finite dimensional vector space. K vector space. And nothing about finite also, definitions etc. will make sense, but we will because we will deal with matrices etc., rank and so on. So therefore, it is better that we assume finite dimensional vector space. Or more generally, A is any commutative ring. Whenever I say commutative ring, that is always with one multiplicative identity, and V finite free A module. And I just want to put a caution here. When I say finite, it doesn't mean that it is cardinality wise finite. What I mean is finitely generated. And free, of course, you know, free means there exists a basis. So free means there exists a basis. And that basis, I will write it xi I in I. So this I is a finite index set. If you are getting confused, you should take I equal to 1 to n. And I just also want to remind you, commutative is very, very important here, because you might have come across free modules or non-commutative rings where the number of elements in a basis may vary. That means rank is not well defined for over non-commutative rings. So these number of basis elements, they are called rank. Rank of V over K. Of course, in this case, over finite dimensional vector space case, rank of V over K is precisely the dimension. That is, so I will, instead of saying finite free module, I will also keep saying free module of finite rank. Free of finite rank. And many theorems, what you have learned in linear algebra, they can be carried over to many, not all, to finite free modules or arbitrary commutative ring, but not all theorems. And in this way, you can be more disciplined to write better proofs from your linear algebras. All right. So with this, that is our setup. And now I want to recall you what is V star. See the module V star. This is a dual module. That is home A VA. They are homomorphisms phi from the module V to A. These are A linear maps. And these are also called linear forms. They are called linear forms. On V. And now I just want to recall you that this module V and V star, they are related to each other very neatly by the natural bilinear function. So how are they related to each other? We have a map V cross V star. This is a product set to A. Namely, any X and any linear form E. E, I am calling it a linear form. And what can we do? Take the evaluation. So this is very intimate. I will come back to this example again and again, and I am going to generalize this example to define now what are called. So it is very important. We will see during the course that this connection of V is very important to draw good conclusions. All right. So now is it, if anybody has if somebody says that they have not studied over commutative ring, doesn't matter. You restrict to the case of vector spaces. So even I will do that, because as long as the things are not very difficult, they are dicto proofs, then I will write my statements over arbitrary commutative ring. And when they need some special attention to the fact that it is a field, then I will mention it explicitly that this will work only for the fields. And I will keep calling this A as a base ring. A is a base ring. And I will not keep saying commutative. For me, only commutative rings are there. Other rings, I have no feeling for them, essentially. And then I don't know many non-commutative rings other than the matrix rings. All right. So, and the main thrust will be when you talk about a field, I will talk about real numbers and complex numbers. And I will design my definitions and statements so that I want to prove in both the cases together, though they are different. They are different cases. And you must also notice that if I don't know which exercise that in affine spaces, I mentioned somewhere fundamental theorem of affine geometry, and they differ for this. So such a distinction will come over, of course. All right. So what do I want to do? So I want to show that both these will be fit in our setup very well. Okay. So I am going to assume A is a commutative ring. I will say this time, but onwards. And together with an involution. What is an involution? That involution I will keep denoting sigma. Sigma is from A to A. That is called involution. If it is an automorphism of the ring, A. And remember, automorphism means it's a ring homomorphism. And remember, ring homomorphism for us carry 1 to 1. That is a part of the definition of a ring homomorphism. It's a ring homomorphism which is bijective, and the inverse is also ring homomorphism. That is the definition of automorphism. And involution means sigma square, that means sigma compose sigma is the identity. That is the involution for us. Is that clear? And typical example of involution is the complex conjugation. A equal to C, and sigma is, I will write this. This is the standard notation for complex conjugation. Of course, another example is, see, if I take sigma is identity on any ring, that is obviously an involution. Sigma identity square is of course identity. So this is also an example. So in case of R, sigma you can take IDR. And that is the only choice. You have seen there is no other automorphism of the ring R. Or even for finite fields. I'm not sorry, I made a mistake. Finite field means even if you take K equal to Fp, where P is a prime number, there are no automorphisms of this finite field other than the identity. Remember, I was talking automorphism group is trivial. Trivial in the sense it has only identity. So these are rigid, very rigid. Real numbers, also rational numbers. Also rational numbers, I will take sigma equal to IDQ. And there is no other choice. So the theory will still go on. So if I take R with identity, this sigma as identity automorphism, then you will get bilinear case. If you take sigma with a complex conjugation, then it will become a Hermitian case. That is what I will do it together. And in this case also similar. So, and our thing will work for arbitrary field, not only arbitrary field, arbitrary commutative rings where there is an involution. And now I first want to give you, there are lots of examples of involution we can create. All right. So it is not just only these cases, but some more cases. So I want to write this example. This is very important example that this theory will go on. And in fact, it goes to very important question. All right. Sorry. All right. All right. So this example is a sort of a generalization of the complex numbers. All right. So what is it? So this complex conjugation is a special case of the following example. Okay, what is the case? Now, let us take, because I want to keep my notation. Okay, so let us take A equal to, okay, fine. I want to put A equal to K, but K is a commutative ring, not a field. Because otherwise I will run out of the letters and I don't want to complicate the notation. And B a quadratic algebra. Over A, over K. Now, you may not know this, but of course you know it in without knowing the name. So what does that mean? That means it is a free algebra. But let me ask you first, everybody is clear about when one says algebra over a commutative ring? Definition I'm asking. Hello?
No, sir, I know, but
So can you, Ishan, do you know what is a quadratic what is an algebra over a commutative ring?
yes, it's
What is
another
it?
ring. It's a ring with a ring morphism from, so call that commutative ring R. Okay.
Mm-hmm.
So a ring morphism from R to S constitutes
R2
S.
F
S for
S.
sun.
Mm-hmm.
Yeah, where S is what you're calling the
R algebra.
R algebra. Yes.
Yes. And both your rings are commutative. See, this will exclude your definition is not general enough. You don't want to consider S as a non-commutative ring?
No, not if you're asking about a commutative R
Okay.
algebra.
But then you will exclude very important ring that we want to study also.
Okay.
So, for example, I will first give an example and define precisely what is an algebra. So, this is a digression about algebra. Many of you have, I've seen many students which come from the university background, they know approximate definition, they don't know precisely. So that is, it is better to recall. So algebra over a commutative ring. Ring, and let me keep it K. So if K is also a field included in this definition, no? You can specialize to K equal to a field. And the example I have in mind is, of course, this ring. Endomorphism ring of a vector space over K. You very well know this is a ring. Yes, please.
Yes, I understand. The commutative thing does not make sense.
I
Yeah, somebody else is talking. Who is talking?
Sir, it's me. I think you need the image to be in the center if it's non-commutative.
What needs to be in the center?
The image of the ring homomorphism. So if you're taking your test to
Image
do
of the
an R algebra.
that ring homomorphism.
Hello.
Yes, I understand. Image of the ring homomorphism, right?
Yes, yes, yes.
Yes, very good. That is correct. So this example we need to include. In fact, my comment is this is the only reasonable non-commutative ring that I know and I want to study.
Yes.
Other non-commutative rings, in my opinion, they are not worth studying because it becomes very dramatic. Anyway, so what is the first of all? Let me recall what is the algebra over a ring. So an algebra B over a ring over K. K is commutative. Is you can define it in two ways, two equivalent ways. So one you define it's a ring homomorphism. So you can algebra over B over a ring K. You think of it as a pair B comma phi, where B is a ring, maybe non-commutative, may not be commutative. This is a typical example. And phi is a ring homomorphism from K to A, K to B. And remember, ring homomorphism will carry 1 to 1, 1K to 1B. This is a part of the definition of a ring homomorphism. Ring homomorphism such that image of phi is contained in the center of B. This is the center of B. That is what this Vaidehi said. Well, but still, where do you get this condition from? That is I want to explain. Right, this is correct. This is a very good correct definition. And this example is our example fits here very well because we have a map here from a field to the endomorphism ring of a K vector space. And the image are precisely what are they called scalar matrices or scalar homomorphisms, no? So scalar matrices, and that precisely is the center of this ring. And that fits very well. But this is okay. And this phi is unique. This phi is unique and this that is given to you. So this phi is called the structure homomorphism. Homomorphism of the K algebra B. That defines the structure of a K algebra on B. For a given ring, there may be many homomorphisms. And with respect to each one of them, many homomorphisms which will have this property. And with respect to each one of them, they will give a different algebra structure. All right. So, other way, equivalently, so we are defining a K algebra. Equivalently, B is a ring. B, let me write now a little bit more precise. B equal to B plus dot is a ring. That is first. Second, this B B with B plus. This is an abelian group because it's a ring. So this is an A module, K module. This is an abelian group and this is a K module means extra thing we have given is that is there is a scalar multiplication of K on B plus. That is, you think of that is a map from K cross B to B. And that obviously we are denoting A comma X goes to AX. That is just a notation. And this should satisfy several properties. That it is compatible with this plus. That means whether you add elements of B and then multiply by scalar or multiply scalars first and then add later, that those results are equal. Similarly, the last one 1 times K times any X is X for every X in B. These are also some people who study non-commutative rings and other things, they call it a unitary module because for many of them the modules are not unitary, but we don't go into that kind of generalities. So, and then the third one is this multiplication and scalar multiplication, they are compatible with each other. So this is a ring multiplication, remember, and this is a scalar multiplication. So the ring multiplication in A, B, the ring multiplication in the ring B and scalar multiplication of K on B are compatible. Compatibility is very important issue. Even in the life, compatibility is very important issue. So let us recall what does it mean. So here also we have seen compatibility of the scalar multiplication with the plus. That we did it in vector spaces so many times, no? So what will this mean? So that means for every now scalars A, B in K. These are scalars. These I keep calling them as scalars. And every xy in B. Any two elements in that ring B. What can we do? We can either multiply A by X, B by Y, and multiply in the ring. This multiplication in the ring B. You see, this is a scalar multiplication. This is X in B, A is in K. Therefore, this is in B. This is in B. So we can do this. On the other hand, we could also do that. We can multiply A and B in the ring K and multiply X and Y in the ring B. So this is a ring multiplication in B and this is a scalar multiplication. These results should be same. And now this is a very powerful property. This will tell you that actually what we are, the first definition, that this is contained in the center, that will follow from this definition. So that if we check it, these two definitions are equivalent. And then how do you get that phi from this? Now it is clear how to define phi from K to B. How can you define phi? A going to A times 1B. Now you check that this, if you define this, This is the scalar multiplication. And because of this compatibility, this will become a ring homomorphism, and the image will go inside the center. And this will be then the structure homomorphism for this algebra K. Conversely, if you have this, then you can conversely if you have this, then you can define also the same. So these definitions are equivalent. This is exactly similar checking as what we have done in case of a group actions, the operation homomorphism, operation maps, and the action homomorphisms. Similar checking, nothing more. So that is what the algebra means. Now, what is the other adjective there? Free, quadratic. Quadratic algebra means it has a basis which has two elements. So quadratic B is quadratic K algebra means B is a free K module of rank 2. That means there is a basis of B over K as a K module and free. Rank is 2. And how do let me first give you these. There are lots of examples. These examples actually arose from the studying quadratic equations. So, example. Let K be a field. And x square plus bx plus c. This is a degree 2 polynomial over K. And monic. We can always make, because it's a field, you can make a polynomial always monic. This is degree 2 monic polynomial. So, and then I consider now the polynomial ring Kx. This is a polynomial ring, and then take the ideal generated by this polynomial there. This is an ideal here and proper ideal. And then I go modulo that. So I consider B to be this. Kx, B is this. Kx modulo this ideal. And this is now, I will denote small x to be the image of capital X under this homomorphism. There is a natural onto map here. It's a ring homomorphism, natural surjective map. If you call it pi, this capital small x is the image of x under pi. That means this x equal to pi x. And then it is obvious what is x square, what is small x square. Small x square will be equal to minus bx minus c. That is, and then this b is in fact a free K module with basis 1, x. 1 means 1b. That is a typical example of a quadratic K algebra of rank 2. And nothing special about K field here. I could have taken any ring and would have taken any monic polynomial degree 2. And why degree 2? Arbitrary degree. In fact, let me write a most general proposition where you would have studied this somewhere. I don't know when. If you have not studied, please tell me. I will prove it for you. So, any ring, commutative. And capital F, monic polynomial. Monic is very important. A1x plus A0, where this A0, An minus 1, they are in the base ring A, then B equal to AX modulo ideal generated by F, and here obviously imitating that I am denoting small x as the image of capital X in this ring. There is a ring homomorphism from AX to this. This is a natural surjective map pi. That means take any polynomial, you divide by f and look at the remainder, and that is the image. So this b equal to this is a free A module of rank equal to degree of f, which is n, with, in fact, I will tell you a basis, with basis 1 small x up to small x power n minus. Therefore, rank of B over A, I will keep writing like this also, rank of B over A equal to n. Now, you please tell me whether do you know the proof of this or should I prove it? Hello, Ishan. Ishan.
Yes, sir. I think I do know the proof.
You know the proof. And can I replace that f by another polynomial which is not monic? Where is monic playing a role? That is what I want to raise the point, which is of course very crucial point. Do you know whether a monic is very important or I can get away from monic? Please answer my question.
Sir, monic is important since we are working
You
on
can't get rid of monicity.
Because we can perform the division with remainder. This is exactly.
We need.
Sorry.
Hello.
Yes.
Yes. We need monic to like say that division algorithm is working.
I am not able to hear you correctly. Your voice is splitting. You are right. Monic is very important. But for what?
For division algorithm.
Yes. Monic is very, very important for the division algorithm. Division by arbitrary polynomial or arbitrary commutative ring doesn't make sense. But if your polynomial is monic, you can perform the division with the algorithm and write quotient and remainder, and the remainder will have degree strictly less than the polynomial you are monic polynomial there, the degree of the monic polynomial. So in this case, it is n minus 1. So remainder may have degree up to n minus 1. And that is uniqueness of the division algorithm will tell you this is in fact a basis of that this one. So this is the generalization of this. And as you see, when we want to study polynomials, the zeros, etc., this construction is very, very important. This is the first elementary construction, I would say. All right. So that is so what is a quadratic algebra? It's an algebra over a commutative ring of rank 2, and in that case I can make one of the basis element to be 1. This is also another very big important issue which I will not go into more detail, but because it is quadratic, I can arrange so that one of the basis element is 1. Otherwise, it may not be possible for a higher rank. All right, so that is it. So our standard example, C or R is a quadratic, or let me say free C is a free algebra over R over R with basis 1, that imaginary I. Because think of C as Rx modulo x square plus 1. And therefore 1, I is a basis. All right. So what I was saying, I wanted to take a general quadratic algebra and do something. To give you example of conjugation. So therefore coming back there, start with let B be a free K algebra of rank 2, and I will fix a basis with basis 1 and W. So therefore I will look at W square. W square is an element in B, and therefore W square has to be linear combination of 1 and W with coefficients in K. So that will be of the form alpha plus beta W for alpha beta in K. Now I will define a homomorphism from B to B. So with this, and these alpha beta are unique also. So define homomorphism. What can I call it? I want to call it kappa or sigma. Sigma from B to B. And I want to define this as a K algebra homomorphism. Right? All right. So what do I do? Take any element of B that is uniquely written in the form lambda plus mu B. Mu W. Arbitrary element of B will look like this. Lambda mu are in K. And I want to define it by, I will add a formula, and then we will say this formula is not very difficult, but we got it from the conjugation. So I will write this as lambda plus mu W conjugate. This is my sigma. Sigma of lambda plus mu W. And what is this by definition? This by definition is lambda plus mu beta minus mu W. Now this formula, where did I get from? I will tell you where did I get this formula from. Exactly, I am going to imitate what happened in complex numbers and real numbers. All right, so what do I have to do? I want another element in B, no? So what do I do is the following. I want to send this. So in particular, where will 1 go? Can somebody tell me where will 1 go? Now I just have to take lambda equal to 1 and mu equal to 0, and what will it go? Mu is 0 here, lambda is 1 here, so it will go to 1. Obviously that we want it. Where will the basis element go? W. Where will it go? So in that case, lambda is 0, mu is 1, so it will go to W bar, which is by definition, what was the definition? That lambda is 0, mu is 1, so that is beta. That beta is coming from W square. So that is beta minus mu. Mu is 1, so beta minus this. Now do you realize where it came from? This is the analog of the complex conjugation. All right, so you check this, and then we will continue with this, and you explain me why this is maybe the first problem. You can do it in the next week. That where do this expression come from? That is called the conjugation. So when you specialize two complex numbers, when I take I, then beta is what? In that case, beta is 0. So for a complex conjugation case, what is I square? I square is 1 minus 1, right? I square is minus 1. So therefore, that alpha is minus 1 and beta is 0. So this will be minus this. So this is I, and then this I bar, we got it minus I. And then because it's a ring homomorphism, multiplication, etc., compatible, that will match up with this. This is the analog of the complex conjugation, or a more generalization. More than this, I will come back and tell you sometime when we have enough machinery with us. So right now, don't bother much. Just see this. All right, now what do you want to define? I want to define. So remember now our assumption is our base ring is A. A is a base ring, commutative ring, of course, and sigma is an involution, that is an element in OT A. OT A has a ring, and sigma square is identity on A. This is involution, and I am denoting the sigma, therefore by above analogy I will denote sigma from A to A by A going to A bar. Bar means this is sigma. This is arbitrary automorphism, but this. All right, now I have given two modules V and W, A modules. Then the function I am defining, phi. This is a map from V cross W to A. Is called sesquilinear. Sesquilinear if it is linear in first variable and semilinear in the second variable. And semilinear means A will not come out, but A bar will come out. So let me write precisely the definition. It's called sesquilinear. If I will write first in the words, and then we will. So if one linear in the first component. And second, semilinear. Semilinear. I will define what do I mean by this in the second component.
Can I ask something, sir?
Yes, yes. Let me complete this and then you can ask.
Yes.
Let me complete the definition. So linear in the first one means phi of a x1 or a1 x1 plus a2 x2 comma y should be equal to a1 phi x1 y plus a2 phi x2 y, and this is true for every scalar a1 a2 in A, and for every x1 x2 comma y in B. Then it is linear in the first variable. The second semilinear means phi of second variable x, first variable is fixed, and then b1 y plus b2 y2. This is same thing as b1 bar phi x y1 plus b2 phi x y2, and this is also true for all b1 b2 scalars and for all x y1 y2 elements in the algebra B. Yes, that is called, such a thing is called semilinear. That means it's not linear, but bar will come out of the instead of the scalar. Now ask me, Ishan, what was
First, so whenever I have done norms, it has been with R and C. And so the first thing was, why do you not, if you can define conjugation, why do you not talk about norms over fields instead of over fields other than R and C?
you are right, but I didn't want to go through that, because if I go in that, I will not come out so easily.
Okay.
So I wanted to find shortcut, because we have the time limitation. No, that is the reason. You are very right, because this is a norm and it is connected to norm and trace, and therefore it is connected to Galois theory. Yes. Does it satisfy your query?
Yes, sir. I understand with the time constraint this is. Yeah.
Yes. Yes. I just want to give you that motivation, and sometime, as I said also, I will come back to this sometime, whenever I have a chance. But first I want to go the theory led going. So this is not the full motivation, but at least some motivation and then nothing. All right. All right. So remember, in particular, what is the important consequence of this definition is if phi is sesquilinear. So I will write here. In particular, this is very important consequence of the definition. Phi of, if I take ax y, this is same thing as phi of x a bar. I purposely wrote with the gap here. You know why this in particular follows? See, this tells you it will come out in the first variable. So it is a phi xy. And this says that this a bar will come out as a bar of that a bar. But a bar is a bar, and bar of that will be a back again, because it's an involution. Therefore, you know, if I don't write like this, that is what I wrote. And this is the explanation for that. From the first variable, it's linear. From the second variable, it is semilinear. Semilinear means this. And you see these semilinear maps are connected to, if you read carefully my writing, I think one of the footnote in that affine spaces that it is connected to fundamental theorem of geometry. All right, so that is a sesquilinear function from V to W, and the set of all sesquilinear functions. I never told you what is sesqui. If you go and see the dictionary sesqui, the dictionary meaning of this is 1.5. So that means it is, it's not exactly linear, but it's not too bad in the second variable. It will come out as a bar, and then a bar is like a complex conjugation. So that is setting up that notation is very important. So therefore, also I will denote this sesquilinear. A is my base ring, and V and W are the two A modules. And so far in the definition, I never use their free modules. In the definition, arbitrary. This is defined for arbitrary modules. I don't need free for definition. So one should keep that general thing in mind. The definition makes sense more generally, but when you prove theorems, we need to assume something. So when you state theorems, you have to write your assumptions very carefully. All right, this is sesquilinear, and actually, if necessary, in this notation, we will also have to mention the involution, because your ring may have more than one involution. And this, all this definition makes sense with that fixed involution. For example, if I take a field extension and then I take a Galois group and take an element in the Galois group of order 2, all of them are involutions. How many are there, etc., that will depend on what the Galois group is. And so we will have lots of examples. That is what that Ishan was pointing out about norm and trace, and they will arrive from there. But I didn't want to go in that generality. All right. So this is the set of all sesquilinear functions from V cross W to A. All right, now, so you see that this sesquilinear, if I call it phi, any sesquilinear function, that will also the values. When I say values of phi on the pair x comma y, where x is in V, y is in W. I want to show you that these are determined by these values. Then that will become clear soon, but these values are also sometimes people denote by this x, y. This is actually this is a standard notation for the inner product. But sometimes these also denote by this, and when your sesquilinear function is fixed, then you can denote by this. Okay, and when phi is bilinear, that means it is also linear in the second variable. That is precisely the case when sigma is identity. In that case, sesquilinear A VW, this exactly matches with multilinear maps, mult A VW. These are multilinear maps. Multilinear means linear in each variable. All right, so if A equal to C, remember, I have no choice, but I will only take sigma is the conjugation. Complex conjugation. And A equal to R, I have no choice, I will take A equal to sigma equal to IDR. And in that case, we can say complex linear, a complex sesquilinear. In that case, R sesquilinear. All right, its time is coming. All right, so another question I wanted to ask was, do you guys know what is the tensor product?
Of modules?
Yes.
Yes, I do.
How many of, let me just take how many of you are aware of tensor product? I will not use much, but just in case sometime I slip and I use the tensor product, I don't want to make you scared. All right. So I think this time is coming up, and then I will continue this in tomorrow's lecture. Actually, today it was not much, but this is a big motivation. Where are we going to? What we are going to do, and what we will be the next coming up is each. When I say sesquilinear form, that means W equal to V, and then give some examples, and then we will reduce this study to the matrices. And then some groups will arise, matrix groups will arise, and so on and so on. That is how I plan from the next week. There are now 4 lectures only, so I have to be very selective. Today was a little bit more general and maybe boring for some of you. All right, any question?
Sir, I don't know what tensor products are.
So I will not use much. Even if I use little bit, you can ignore it.
Yes, yes, sure.
And even this, I will use when K is a field. And therefore VW vector spaces. So all of you know linear algebra basic. That is what only I will use it. But just to make you aware that this study didn't just start just like that. It is started probably with equations. Because equation was a very old study and still many questions are not answered till now. So in a hope that we can answer those questions, many people have generalized many things. And then many subjects arose. And then people are studying different subjects. So the basic, if you just go back, how does the mathematics got developed? From the polynomials, study of polynomials. As you know, even the number systems came from the polynomials. All right, so any questions? Hello, Pawan. Pawan. Anyway, I will send this to Purnashri and Makaran. Okay, I send Purnashri, I send you the file and I will stop presenting.